So all of the examples of acids that we've looked at so far have been what are known as monoprotic acids. Okay, and monoprotic meaning that there's one ionizable proton, one ionizable H plus, meaning that there's one H plus that can be lost, right? That's where the mono one and then protic meaning proton can be given up. So for example, we looked at HCl, we looked at nitric acid, HNO3, we've looked at acetic acid, CH3COOH, which in acetic acid, this is the ionizable, that's the acidic proton. All the other ones are not. So it's made our discussion of acids and bases a lot simpler so far. However, there are many acids that are not monoprotic, meaning we can have ones that are diprotic and also polyprotic. So you can maybe guess where we're going with this. A diprotic acid is one that can give up or can lose 2 protons when it ionizes. And then polyprotic can ionize or can lose more than 2 when they ionize, right? So poly meaning many, di meaning 2. So when these acids lose, when they ionize, they do so in a stepwise process. So they do so 1 proton at a time, and the loss of each proton successively has its own Ka, acid dissociation constant or acid ionization constant, associated with it. So for example, if we look at carbonic acid, which is an acid that is very common, you find it in your carbonated beverages. So whenever carbon dioxide is dissolved in water, you end up forming carbonic acid. So this actually has 2 protons, and it loses both of them in a stepwise process. So in the first step, here we have our H2CO3. Okay, it can lose one of these protons. So there it is. We take away a proton from this, we end up with the conjugate base. Okay, so this is the original acid to begin with. The bicarbonate ion, this is going to be the conjugate base at the end of that first step. And we have a Ka expression that we can write for that as well, right? So our Ka, and then the subscript 1 tells us it's for the first proton, and that's equal to the H plus times the HCO3 minus divided by the H2CO3. So the product, the conjugate base of that first step, then becomes the reactant for the second step, right? So now the HCO3, this can now act as an acid because it can lose that proton. So when it acts as an acid, it gives up that H plus. It then becomes the carbonate ion that is now the conjugate base of the bicarbonate ion. And we can also write the Ka expression. It would be the Ka2, meaning that it's for the second ionizable proton. It's going to be now the H plus times the carbonate ion, CO3 2 minus, divided by the concentration of the bicarbonate now, the HCO3 with a minus charge. Generally, what we're going to see is that the Ka value for the first ionizable proton tends to be a lot greater than that for the second, right? So it's much larger for the second. And if you had a third and a fourth, the second would be much greater than this third, and the third would be much greater than the fourth, etc. So this should probably be a 2 of these arrows here, as opposed to just 1, because it's much greater. This Ka value here usually is much larger than the Ka value for the second. This tends to be much smaller. But the point here is, it happens if there are more than 1 proton, if there's more than 1 proton that can be ionized, it does so in a stepwise process. All right, so we looked at carbonic acid just now, for instance. Okay, so the Ka value for the first proton is 10 to the negative 7. For the second is 10 to the negative 11. So there's, what, 4 orders of magnitude difference in the Ka values. So that's 10,000 times smaller for the second than it is for the first. And in some cases, like in phosphoric acid, where there are 3 ionizable protons, right? The difference here between the first and the second is 5 orders of magnitude, or 100,000 times. And then from the second to the third, it's about the same difference, about 5 orders of magnitude difference as well. So when we have situations of di and polyprotic acids, we can apply the same equilibrium systems. We're going to do so in a stepwise process. So we're told here that oxalic acid, I think that maybe, yeah, so it's written up here. So based on this, we know that it's diprotic because there are 2 Ka values. So it's going to lose those in a stepwise process. We're told, calculate the concentrations of all species present at equilibrium in a 0.10 molar solution. Okay, so we're going to apply the equilibrium principles in a stepwise process. Okay, so we can write out the equation for the loss of the first proton, so H2C2O4, forming H plus, and then we get the oxalate ion, HC2 4 minus, and then we have a Ka value associated with that. Okay, we can write out, we can determine our ice table for this first one. Okay, we don't see water in here right now. It's not really important again, as this concentration doesn't change. We're told we have an initial concentration of 0.10 molar, none of these to start with. Right, we're going to gain X in each of these cases. We're going to lose X in this case. At equilibrium, we have 0.10 minus X of the starting acid. We have X for the product side. So we can now write out the Ka expression. This is Ka1 for this. H plus times HC2O4 minus divided by the H2C2O4. I'm going to substitute my values in here. Okay, and then what we can do again, we can make our approximation that X is small. Okay, so this then would mean that this entire thing would be equal to 0.10 to simplify the calculation. So we end up with X squared over 0.10 is equal to the Ka1 value, which is 6.5 times 10 to the negative 2. And then we solve for X. So X here would be equal to, if we do the math on it, we would see that X is equal to 8.1 times 10 to the negative 2. Okay, so before we go any further, let's test the approximation to see if it's valid. So we're going to take our X, 8.1 times 10 to the negative 2, divided by the original concentration, 0.10, times it by 100. And if we do that, what we'll see actually is the percentage difference there is actually 81%, right? So that's more than 5%. Okay, so that means the approximation is not valid. We actually have to go through and solve this using the quadratic equation. So this is not going to work. Okay, we can't use this approximation up here. Instead, okay, we're going to have our X squared over 0.10 minus X. We have to now keep track of the X in the denominator. That's still equal to 6.5 times 10 to the negative 2. We rearrange our equation. Okay, so we end up with X squared plus 6.5 times 10 to the minus 2x minus 6.5 times 10 to the minus 3. And that is equal to 0, right? This is your quadratic equation. And we have to do that because the approximation isn't valid. And then that leads to, we solve it, X would be equal to 0.054 molar. Okay, and that's the value for X that we get. So what do we end up with at equilibrium? So the X there we just found was what, 0.054. So we can substitute that in now. So we just found X 0.054. So minus 0.054 plus 0.054 plus 0.054. So then at equilibrium, we have these exact concentrations. And then this here would be equal to 0.046 molar. So the product, one of the products here in this first ionization ends up being the starting point for the second one, right? So now we have our HC2O4 minus ionizing to give us our H plus and our C2O4 minus. We know that this starting concentration now initially, I'm sorry, is going to be what we just calculated, 0.054 molar. Okay, and we still have also our H plus concentration, 0.054, right? That was produced from up here. We don't have any of the C2O4 minus, so that's 0 to start with. And then we can do our same thing. So now we're going to gain, we're just going to call this Y, just to differentiate it from the X we used previously. We're going to plus Y here. We're going to subtract Y. So at equilibrium, we have 0.054 minus Y. We have 0.054 plus Y, and here we have Y. So we can write out the Ka expression for this. This is going to be our Ka2. All right, so we have the products, which are going to be Y times 0.054 plus Y divided by 0.054 minus Y. Okay, we can make our approximation again. So Y is going to be close to 0. So we can simplify this. We can say that Y times 0.054 divided by 0.054, and that's equal to Ka2, which we can look up. That's 6.1 times 10 to the negative 5. So the 0.054s cancel out, and we end up with Y being equal to 6.1 times 10 to the minus 5. Okay, so what we just determined there was the concentration of the C2O4 minus. What we also need to do, right, we need to check our approximation. So if we check the approximation, so we're going to take that Y value and we're going to divide it by the original amount that we started with, which was 0.054. And this is for the second ionization times 100. And then that ends up being 0.11%. That's less than 5%. So that means our approximation is valid. So we end up with Y being 6.1 times 10 to the negative 5 molar. So what we've just done now is we've determined at equilibrium for the HC2O4, we're going to have 0.054 minus 6.1 times 10 to the negative 5. Okay, so that is going to be equal to, again, 0.054. That's the concentration of the HC2O4 minus. The concentration of the H plus, so this one now, would be equal to 0.054 plus 6.1 times 10 to the minus 5, which again is going to be within rounding is going to be the same. So the concentration of the H plus is 0.054 molar. The concentration of the C2O4 2 minus is just simply equal to the Y, which is 6.1 times 10 to the minus 5 molar. These are all molar concentrations, by the way. So let's see, those are the three species. We forgot, let's see which one. We need the original oxalic acid, right? And we calculated that up here at the beginning, 0.046 molar. So the H2 C2O4 would be 0.046 molar. So we can go through, even though we have a diprotic acid, we can still calculate all of the concentrations of all the species, but you need to do it in a stepwise process, right? Applying the equilibrium principles to each of the steps, and then the product of the first step becomes the reactant for the second step, and we're doing the same equilibrium stuff on it.